Okay. So in this session, we are going to have three speakers, and under the session title of Molecular Imaging 5, Next Generation Molecular Imaging. This is the only session which does not have any change of the room. So maybe in the afternoon of the third day, so the audiences are a little bit sparse. So, however, the important people would have been here. So the first speaker is Dr. Jae-sung Lee. He's going to talk about the new generation molecular imaging technology, especially small animal PET MRI. He's from Seoul, Korea.
Okay, thank you, Professor Lee, for your kind introduction. So as Professor Lee, introduced, I'm gonna talk about new generation, the molecular imaging technology, the small animal, the PET MRI. I'm Jae-sung Lee from Seoul University. So let me, disclose, my complete interest on this topic. Actually, I'm the co-founder of, the Brightness Imaging that has the partnership with, Aspect Imaging for the providing simple, simultaneous, preclinical PET MRI systems. This is outline of my presentation. So in my presentation, so I will start with so what are advantages and technical challenges and solutions for simultaneous PET MRI imaging, and then let me introduce you to the currently available the PET MRI systems in the market. And I will, I'd like to share, our experience on the animal PET MRI applications in various molecular imaging researches. So let me start with, what are, advantages of MR imaging relative to X-ray CT. So if we use MRI instead of X-ray CT, so that we can eliminate radiation dose from X-ray CT. Another important thing is that MRI has better soft tissue contrast than X-ray CT. So as you can see, in this the comparison between the mouse brain CT and T280 MRI. In the respect of physics, the importantly, that we can simultaneously, PET and MRI images together, although it is impossible in the X-ray CT and the PET images. Then why the simultaneous PET MRI imaging is important in animal studies? The first, I can say that we can reduce the scan time and the amount of the anesthesia that is required for the animal imaging studies. And because because we can acquire the image simultaneously, the output images has better the spatial correlation between the images. And simultaneous assessment of the biological parameters is possible, as you can see in these examples. Actually, that in the left images, the tubing group compare the brain activation by the oxy-15 water PET and functional MRIs. And that it has been also shown that the investigation on the neurovascular coupling to the dopamine D2 and D3 dopamine the receptor occupancy is also possible. So using the simultaneous PET MRI scanners. But that there are difficult technical challenges in the PET and MRI integration. The one of them is the limited space for PET MRI installation and for the PET detectors the inside of MRI board. Actually, when we developed very compact the silicon PM-based PET systems, we used the Bruker 7 Tesla MRI. Actually, this Bruker 7 Tesla MRI had the inner diameter of gradient coil of only 116 millimeter. So the space inside of MR is very tight. So we need to develop very compact PET systems. Another challenge is the interference between the PET and MRI. So actually, that the high main magnetic field of MRI can perturbate the electron transport inside of conventional photomultiplier tube, and the time varying the gradient to field can induce heat and vibration in the PET component. Of course, that the RF pulse in MRI interfere with PET electronics, as you can see in the PET signals that we have acquired using silicon PM PET detector. That was some periodic noise added on this PET detector signals. There is the interference in opposite direction. I mean that some the scintillation crystals used in PET has some components that can perturbate the main magnetic field and can cause susceptibility artifact. For example, some the PET scintillation crystals like LGSO and GSO, because that they contain the gadolinium component in these scintillation crystals, it can cause this kind of the MR image distortions. And because we use metal for radiation shielding, that radiation shielding materials used in PET can cause eddy current and susceptibility artifact as well. Of course, the PET electronics and cables can also interfere with RF detection if we do not design very carefully. So let me show tell you some solutions for the reducing this interference between PET and MRI. Most of all, that we should use MR comparable the scintillators like LSO and LISO, and the non-magnetic component in PET electronics are the preferred as well. And some RF shielding of PET component with modular design is useful for the minimizing eddy current, as we showed in this example. Sometimes that the differential PET signal readout to minimize the effect, or is useful for minimizing the effect of RF interference. And sometimes we use low pass or the notch filters to suppress the RF noise. And most importantly, instead of using the conventional photomultiplier tube, we should use solid state photosensors like avalanche photodiode and the silicon PM. Especially the silicon PM is now a kind of the workhorse for the preclinical PET MRI systems. The silicon PM PET, the insert, has been developed for about 10 years or something like that in the academic field. So actually, that the first generation, the silicon PM, the PET systems for small animal, has been developed, using the clinical, the MRI scanners, because there is the huge space for testing new electronics. But that for last the several years, so second generation the silicon PM PET systems that has been developed to be combined with very compact the animal dedicated the MRI scanners. So one of such examples is our system that was combined with Bruker 7 Tesla MRI, and the Canadian groups also has developed a similar system, so based on the 7 Tesla MRI. So these systems, show very good MR comparability. I mean that so this is the data that we have acquired using silicon PM PET and MRIs. So these images, these are the MR images acquired without PET inside of MRI, and you can see that is not much different from the MR images acquired using with the PET insert inside of MRI while we turn on and turn off the PET scanners. And the silicon PM PET also shows the very good the EPI the stability measurement. Actually that the x-axis is the image number, the time, and the y-axis is the signal intensity. So that it has quite stable the EPI the measurement. And that these silicon PM PET systems showed quite comparable the performance as conventional the photomultiplier too, as we showed in these papers. So currently that several the companies are providing the commercial the small animal the PET MRI systems. So all of them are based on the silicon PM. So the three companies are now the providing the total the PET MRI systems, and that the Cubress is now the providing the PET insert only for the existing the MRI users. But I should say that still there are the PMT-based the sequential systems also the available. So from now, let me show you some of the examples that we have acquired using simultaneous PET MR the systems. So actually that these images were acquired using silicon PM PET and 7 Tesla MRI. So in which we could the assess the brain tumor. So using carbon 11 methionine, that was acquired simultaneously with T2 and FLAIR and the DWI MRIs. So we are doing many the inflammation was related images. So this is one of such example of mouse arthritis model. So so these are the simultaneously acquired PET MRI images from the normal mouse, FDG PET in normal mouse, and this is the KB model, the mouse that is a kind of the arthritis the models. Okay. And we are also collaborating with Professor the Haewon Yeon and Professor the Byung-Chul Lee to test the novel TSPO imaging trace in the LPS-induced inflammation models. So you can see that the LPS the induced inflammation is well localized using the simultaneously acquired the MR images. So my colleagues are now the very active in developing the multimodal the imaging proof, and we have found that simultaneous the PET MR is quite useful for the cross-validating these PET and MR the signal changes. So my colleague Professor Yoon Sang Lee has developed the copper 64 the labeled the encapsulate the iron oxide nanoparticle. So these are the PET MR images before the injection of this tracer, and these are the 1 hour post injection data and the 4 hour post injection data. So in the MRI because copper cells in liver the capture this tracer, so you can see the signal change in the liver that get dark in these images. And we can also find the high activity of the radio tracer in the same regions like that. He also attached the folate to this the copper 64 the iron oxide. So so actually these are the PET images acquired the before injection and 1 hour, 4 hour, 8 hour, 24, 48 hours after the injection. So you can see that the uptake in the tumor regions is very clear, and that it can continue until the 48 hours later. And this uptake was also found in MR images here. So actually that you can see the MRI signal was also the changed and was quite stable until after the 48 hours after in this study. And because it was simultaneously acquired, we could confirm that these signals are from the same site. This was another study using the dual modality, the imaging proof. Actually, the professor Jae-min Jung, another my colleague, that has developed similar proof, but actually this the iron oxide was labeled with man nodes for lymph node targeting. So if we so actually that this is one of lymph node of mouse before the injection of this dual modal the proof. But after 10 minutes the post injection, so we can see the clear change of PET signals here, but the MR signals was a little bit equivocal. But after 2 hours post injection, both of the MR signals and the PET signals were very clear. So in this the experiment we can also confirm the signal change of PET and MRI, and we could also find that there is some sensitivity difference between the PET and MR studies. So if we reduce the size of iron oxide, we can do the blood pool imaging as well. So my colleague Professor Yoon Sang Lee labeled 5 nanometer core the iron oxide with copper 64. So these are the images acquired the pre-injection and the 10 minute and 1 hour and 24 hour so post injection. So you can see the movement of trace from the heart to the other lesions like that. And if you compare this pre-injection data and these post-injection data, so you can see very the clear change of the MR signals, both of MR signals and PET signals that was well matched with each other because they was assessed by the simultaneous PET MR imaging. Okay, so let me sum up the presentation. So I told you that the simultaneous PET MR acquisition has several advantages over the sequential one, and it has been demonstrated that the feasibility of simultaneous PET MR the system based on MR comparable the compact silicon PM PET the insert. And I have showed you that it will be useful for the investigating rodent model of disease and for especially for the cross validation of bimodal the imaging proofs for PET and MRI. Okay, thank you.
Any comments or questions? We have plenty of time. So yeah, please. So please use the microphone and identify yourself.
Thank you for the excellent talk. My question is not really regarding the probes. Let's say if some new imaging facility, they want to buy a brand new PET MR system. Which one you listed you would think is the best one? The PET MR system that you listed from all different vendors.
Oh, yeah.
I hope nobody's here.
Yeah.
But which one would you pick if you have to buy one?
So you mean that what is best?
Yeah, best. There is a conflict of interest. He has.
I have conflict of interest. But that let me explain you each of the systems. But that will be fair.
Yeah.
Okay. Yeah. So that I think each of the systems has pros and cons. The Bruker system has very large bore. So if you have enough money and if you need to scan the large animals, I think you should choose the Bruker system. And the MR solution and aspect imaging system has the smaller bore. And these two systems are based on, I think this is based on 3 Tesla MR maybe, and this is also 3 Tesla or the higher one. So if you want to higher the magnetic field, you can choose this. But actually, because these are the superconducting magnet, the based ones, actually it require some maintenance cost. Yeah, but the aspect imaging system is based on the 1 Tesla permanent magnet. So it is cheaper, and the maintenance cost is lower. So based on this kind of information, so you can choose one of them. Let me try to be fair.
So, continuing that question, actually there are differences of the Teslas between MRI system, and some companies are using 3 Tesla, and you are using 0.5 Tesla.
1.0 Tesla.
1.0 Tesla.
Yeah.
But then what kind of criteria should we use to choose between those the Teslas?
Yeah, so so this is my only the personal opinion. But if you have more interest in the MRI, that you can choose better MRIs. But if you mostly have interest in the localization or better soft tissue contrast based on the MRI, and if you are nuclear medicine guys, so I think that I recommend you to choose the cheap and the system without the high maintenance cost.
What about the organ difference? If you're interested in brain PET MRI studies, 3 Tesla is needed, or?
For brain studies, if you want to do some functional MRI or something like that, I think high Tesla is better. Higher Tesla is better.
Mm-hmm.
Yeah.
Okay, please.
Hi, great talk. Just on a similar question, there's some very, very high field small animal MRI. Are there many limitations to, say, a 9 Tesla PET MR, small animal, or even a 15? Because you spoke about the susceptibility artifacts and eddy currents. Do they scale, and is there any advancements taking place to remove them or reduce them?
Actually, we have the tested these PET systems with the 7 Tesla and 9.4 Tesla the MRI as well. But actually, so we couldn't not see any much difference. So I think that it will be also possible to do it with the much higher Tesla, but we should be very careful about the PET component.
Okay, please. Please use your microphone.
Do you have any experience with simultaneous MRI PET with utilization of MRI contrast agents?
Contrast agents.
Contrast agents.
This means gadolinium complexes, not molecular contrast agents, not iron.
We have just used the iron oxide, nanoparticles, because the chemist, has focused on this kind of the tracer development. So, but maybe that some others has done that kind of studies as well.
I'm just asking if you have experience.
Yeah. Is there a bond here? No. So maybe he has naturally the experience. You can ask him.
I know. Thank you.
So, I think among the learning objectives, the first one, advantage of simultaneous. The various advantages of simultaneous PET MRI is now well known to the audience. And what about the second question? Advanced scintillation detectors. So is this the kind of cutting edge? Is there further any kind of room to be improved for further in terms of the detector, scintillation detectors?
Let me see. Yeah, so
I mean the next version. Should we wait until the next version is coming, or should we buy right now?
Yeah, so you know that the advanced, the more advanced PET detector would be the time of flight PET detector, but the time of flight information does not work for small animal the imaging studies, because small animal scanners is too small. So that if we have the 20 picosecond timing resolution, something like that, there is too much better for the current systems. But if we can have the kind of really great system within the 10 years or 20 years, we can also improve the small animal one. Yeah.
Okay, if there is no more question, thank you. Thank you very much. Then we are going to move on the next topic, molecular imaging translational PET MRI. So by Professor Gary Egan from Monash University here, Melbourne.
Thank you, Mr. Chairman. Good afternoon, everybody. I'd like to start off by acknowledging financial support we've received from Siemens Health and Ears for some of the work that I'm going to be presented, and to just share with you where we actually are in Melbourne. Monash University is located about 20 kilometres south east of the city. So you can see this is the university campus, here's the city, here's the Australian synchrotron, and then here's Monash Biomedical Imaging Facility. And a little bit more close up, the Australian synchrotron with the visitor centre here, and an external beamline, which is really one of very few in the world. An imaging and medical beamline extends out 100 metres into a large animal imaging facility that will also fairly soon be doing human clinical imaging and irradiation. And then that's connected into the Monash Biomedical Imaging Facility. So this is probably a world unique facility combining conventional biomedical imaging, MR, PET, CT, together with synchrotron imaging, and in particular phase contrast X-ray imaging, which is a great technique for looking at soft tissue contrast. So this is the outline of my presentation. I'm going to start off by giving you a little bit of a run through on some of the developments we've done, technical developments we've done using a PET MR, that's the Biograph MMR from Siemens. Talk a little bit about the stability of the system, some attenuation correction work, motion correction, and then some image reconstruction techniques. I'll then talk a little bit about some translational applications in some large animal models, in an ovine model of brain injury and a canine model of brain tumour. And then at the end I'll expand that into human imaging with a focus on brain imaging, and talk a little bit about some functional PET work that we've been doing in the last 18 months or so. So here's an overview of the MR PET scanner from a systems perspective. We've got the PET scanner here along the top and the MRI scanner along the bottom. And I think most people really think of just collecting MR images, collecting PET images, and then registering them at the end and getting great anatomical localization from MR for interpreting and analysing PET. But in fact, there's a lot more things that you can actually do, as well as some of the sort of, if you like, technical hurdles to be overcome when you just have MR and PET. And so you have to actually be able to reconstruct the PET using an estimate of attenuation correction, a mu map. So that, in principle, ideally would be derived purely from MR sequences. And then secondly, you can try and improve the PET raw data set by correcting the sinograms or the LORs as they're acquired using motion information, real-time motion information from the MR. And then once that's reconstructed into images, then thirdly, it's of great interest to look at how you can simultaneously analyse these two data sets, ideally when they're dynamic data sets and not just static images. So that's been our challenge that we've taken on over the last 18 months. But the first thing we did to determine that the scanner would work in the way we wanted, i.e. simultaneous functional MRI and dynamic PET scans, We firstly tested the stability of particularly the PET side of the scanner. That was a key question. And to do that, we took on the FBurn functional imaging protocol over 30 minutes, which is an EPI sequence, which really drives the magnet pretty much as hard as you can. And then over 30 minutes had essentially the PET scan acquisition running, and then beyond that for another 30 minutes, and to see how the counts in the PET images were tracking over time, whether they were being affected essentially by the heat generated from the gradients in the magnet. So that was a key question. And to look at that, we basically looked at the FBurn analysis to look at the actual quality of the functional MR scans, and then secondly looked at the PET data reconstructed into 1-minute bins and look at the stability of the mean signal across that field of view. So this was using just a germanium-68 phantom, cylindrical phantom in the scanner. And here you see the results of that. So firstly, the FBurn data up the top, 4 different 7.5-minute functional MR runs. And you can see here very low RMS, very good stability on the mean, grayscale value within these bold images, and then a couple of other measures just showing great stability over 30 minutes. And then of particular interest was to look at the mean PET image intensity in 1-minute time intervals. And you can see here that it's less than 0.5%, in fact over 90 minutes. And there's no discontinuity when we look at the turn off of the gradients at 30 minutes. So that's of quite serious importance. We're very happy with that, less than 0.5% of signal variability, if you like, in the PET imaging. Okay, the second point is to talk about attenuation correction. And of course, most people would use the PET CT or the CT from PET as the gold standard. Obviously, they're not quite the same energy as gammas coming out of PET annihilation, but there's been a lot of work to show that you can now get CT attenuation maps extrapolated out to half an MeV for PET image reconstruction. And of course, here's some work done by a couple of groups 3 or 4 years ago, showing with both atlas-based approaches and compared to an actual CT-based PET image reconstruction, and then a ultra-short TE MR scan, which is essentially looking at bone with MR, and comparing that to the reference PET scan, PET CT scan. You can see that some of these pseudo-CT scans using atlas-based techniques are very good, whereas at that stage the MR-only UT scan was providing very large errors in the PET image reconstruction. And then further elaboration of that using a Dixon technique, and then Genesis as a sort of an MR atlas-based approach. And again, you can see errors in these difference images compared to the reference being the PET scan constructed from the PET CT, the original PET CT. So it's a sort of a problem that's been to a large extent solved, but there are still errors, particularly around in the cortex, if you're doing brain imaging using MR PET. So we tackled this problem ourselves, and we extended the work done. And in fact, Jakub Baran, who's a PhD student with us for a couple of years from Poland, did a lot of this work. It was great work. He took a huge amount of work to manually segment 5 individuals into essentially 6 different tissue types, as you can see here on the right. So as well as SPM-based segmentation of grey, white and CSF, he also then manually segmented bone, soft tissue and air to come up with a technique that's based on UTE MR scanning and other MR contrast of a segmented UTE approach. So it's quite a lot of work. And then he compared that again back to a reference, just standard UTE, pseudo-CT, and then the 2 techniques that he worked on with a small variation between those 2. And you can see the images, if you like, these mu maps that are calculated actually compare very favourably to the reference. When you reconstruct the PET images and then look at the errors of the reconstructed PET against the reference, you can see that these segmented UTE images now have errors that are down less than 3%. So that gives us confidence that the PET images we're getting from the MR PET scanner have very good quantitative accuracy, or at least, you know, getting to the point where we think we can work with them fully quantitatively. Okay, the next point is to say how could we use more of the MR information to improve PET images. So here it's about now looking at all the MR sequences that are being acquired during a PET acquisition and use that information to rebin the sinogram data to do the PET reconstruction. This is work that Xiaolin Chen has led. He's the head of the MR Image Analysis and Methods team at MBI. And most of the scans take a few minutes, as you see in this group of different images here, but some of them are much more rapid, i.e. the bold EPI sequences, which give us images every 2 or 3 seconds. And so in that sense, we can really very rapidly track head motion of a subject in the scanner and be able to try and correct for that. So here's an example of some work that Xiaolin did looking at essentially a phantom study. So it's a brain phantom, and you see here over about 40 minutes the phantom being repositioned at different time intervals. In fact, it's clearer over on this side, where there are displacements made of the phantom and then further displacements in a sort of systematic way whilst there's a range of MR sequences being acquired. And then developed a technique for using all of these MR measures to motion correct this simulated head motion. And you see here on the top row the results of that brain phantom reconstruction, where this is the non-motion corrected brain phantom PET images. This is the reference here on the right, which is just a stationary static. And then in the middle you see the improvements that come about through using both motion correction of the sonograms and also for the mu map that's calculated for the reconstruction. And then in a human subject, again simulating some motion, you see here the reconstructions done without correction for motion and with correction, and it's, I think, very pleasing to see that we can generally correct for that motion quite well. Now here in the bottom row is supposed to be a couple of videos, but they're not going, so I'll just have to let them sit. And on the right is a head curve showing counts in the brain as a function of time, where in the first plot along the top you see, in the plot here, which is digressing slightly, you can see that where there's been some head motion, we can see that this involves an artifact in this total number of counts in the brain image as a function of time. But after the motion correction is applied, which is done as I described, you can see that this, as we would expect, has a smooth increase in brain counts as a function of time. So I think it's further evidence to say that this motion correction applied to the raw PET data helps to clean up and improve the quality of these dynamic data sets. Okay, so the fourth aspect of our technical development work was to look at, in fact in collaboration with the group in Jülich in Germany, with Jürgen Scheins and John Schaar in Germany, was to look at modelling, in fact, the full line of response geometry of the scanner rather than, in a sense, compressing it down into axial compression of lines of response, and also to model in detector gaps within the actual geometry of the scanner. So this is a technique that they've developed in Jülich. It's, I think, really interesting, geometrically, computationally very challenging. They retain all of the possible lines of response within the system, and so it leads to much longer computation times. But recently they've increased the efficiency of their algorithm in such a way that we decided to have a crack at using this for the Biograph MMR. And here you see some results of, firstly, the brain phantom with FDG. It's called Presto, this reconstruction technique. And you see here the reconstruction of this brain phantom image using Presto compared to the standard Siemens reconstruction, point spread function reconstruction with span of 11. And there are different numbers of iterations in these two iterative algorithms, but nevertheless, I think it's sort of promising that this more geometrically based modelling of the detector array and the detector of elements is providing better quality images. And then in the case of a human subject, you see here on the right, again the direct Presto reconstruction versus the Siemens. And in fact, we felt, just based on radiological visualization of this, there were some aspects of the Siemens reconstruction that weren't as accurate as we believe they could be with the Presto recon. So this is where we've got to in terms of developing the technology for, if you like, taking full advantage of the dynamic nature of the two data sets. And I'd now like to share with you some of the applications of this technology. So we have two animal models that are using the Simultaneous scanner. One study which is a lamb model looking at brain injury, intrauterine growth restriction model, and the second is a canine model of brain tumour, sporadic brain tumours in companion animals. So the first, which I'll briefly summarise, is essentially a group at Monash Health in Melbourne, Graham Jenkin and Atul Malhotra, who have been doing a range of lamb studies to look at ligating one of the umbilical arteries in these lambs in utero at 88 days, and then delivering these lambs prematurely at about 128 days, and essentially looking at brain injury in these lamb models. And it's to model human, if you like, insults and underdevelopment in utero, as well as preterm diseases, and particularly lung diseases associated with preterm deliveries. And one of the observations that was published a few years ago was that there's actually been observed to see A-beta plaque deposition in brain-injured lambs and in this model, and so this is some histological data that was evidence of that. So we thought we would use this model with MR PET and look to see if we can localise plaque formation, A-beta plaque, in the lamb brain, and also, as in sense, in a broader sense, to develop a number of biomarkers to investigate brain damage in this premature, in this lamb model. So here's the protocol. This is a procedure that's done in utero with surgical ligation of the one of the umbilical arteries. You can see here that the lambs are born smaller than a control lamb, and then they're maintained from 123 days on in a premature NICO unit, very much modelling what's done with human babies. And then at essentially about 135 days, they're sacrificed and the brains are analysed in detail post-mortem with histology and also with ultra-high field MR. So the protocol is just again shown here, delivered 126 days. We then, within 2 hours, have an MR PET scan done, and then after another 8 to 10 days, have a subsequent follow-up with pathology and as well ultra-high field MR. And so this work has been led by both Mike DeVere, who heads the preclinical imaging team, and Richard McIntyre, who's the chief radiographer at NBI. So here's some of the initial results. I think it's really interesting that with this type of technology, and I'll try and, yep, so that's worked. We can both collect diffusion data, you see here on the right, so diffusion weighted MR, and you see here in a control in the top panel versus a fetal growth restriction lamb model. You can see significantly greater white matter development even at this early stage in the lamb. And on the right was then a video of that data. And then here, these are regions of interest in the FBB PET scan to look at localisation of plaque formation and compare that into the controls. So localisation with the MR structural images greatly assists in identifying and measuring within these regions. The second translational study, as I mentioned, was a dog study, and this is led by a couple of colleagues from CSIRO based in Brisbane, Stephen Rose and Simon Puttick, also at UQ. And their interest is to look at understanding some of the characteristics of human glioma using both a rodent and dog translational model to human. So they've developed some antibody-targeted diagnostics as well as therapeutics. And I guess the real strength of doing this in a larger animal model, as they show here in this slide, is that compared to a human brain, a mouse brain down here, there's a hugely greater amount of territory to be able to investigate with the dog and to translate to human. So this work has been done in conjunction with a veterinary service across Melbourne. This is Sam Long here, who has now scanned about 70 or 80 dogs at the facility. And the question, I guess, is these dogs present as companion animals with a unusual behaviour, query brain tumour. They're referred for an MR scan, and then about out of that group, there's been 7 or 8 who have actually been identified with glioma and are now going on into further aspects of the study. So it's a great opportunity to take advantage of this community-based animal model, and having the sort of referrals set up from the veterinary service has been a key part to the success of this so far. But there are some challenges with this study, which I'll come on to shortly. As you see over here on the right, here's a dog head image, as you can see, a pet image. But that image requires good attenuation correction if you're going to get good preclinical model pet images. You can see a whole range of other MR contrasts here, diffusion, T2 weighted, and then other contrasts that can be mapped directly onto the pet. But there is a challenge, as shown in this slide, of how to get good quantitative pet images out of the MR pet. Based on the CT scan here of this animal, you can see it's very dramatically different than the calculated attenuation map using MR-only contrast. So that still remains as an unsolved technical challenge for us. Okay, the next part of my talk is moving on to human imaging. And one of the areas that I thought would be of great interest using simultaneous MR PET is to look at dynamic brain metabolism. And going back some years ago, there was a study done over at MGH by this group here. They published it in 2014. And it turned out that no one had ever previously published looking at brain functional metabolic maps using a single FDG infusion. In fact, a slow infusion over 60 or 90 minutes. But to be able to essentially do what is now done with functional MRI, where in one scan session to calculate and generate activation maps, if you like, or brain metabolism maps. But they showed here in this very elegant study where they infused, as I say, over about 80 minutes, a slow infusion of FDG, and after about 20 to 30 minutes they got more or less to a steady state. And then in brain areas such as here in the visual cortex, where they were given, when they were giving a visual stimulus to subjects, you could see that in the visual cortex, compared to other whole brain measures, which were just rising in a constant rate, there were increased levels of glucose metabolism in the visual cortex as the infusion was occurring and as the visual stimulus was presented to the subjects. So if you take the derivative of this curve here, you then can see it more clearly that when the visual stimulus was on, as shown in the grey bars, you can see this increased rate of glucose metabolism. And in fact, you can take venous blood samples, and given that the glucose metabolism modelling simplifies when you go into a steady state, you're able to calculate quantitative maps for FDG using this approach without doing arterial sampling. In fact, the effect sizes are quite big. They showed about 25% signal increase in the visual cortex with this slow infusion. So we thought this was really interesting, and what they didn't do was compare this sort of glucose metabolism map to functional MRI bold contrast maps, and that's been an area that we've pursued more recently, and this is work done by Shana Jamadar and Phil Ward, who are postdoc and research fellows at Monash Biomedical Imaging. And essentially, I've basically said all of this already, but the interest is that bold MRI is really not quantitative, whereas we could get to a quantitative functional glucose metabolism map. The temporal resolution of bold FMR is clearly much better than PET, and that's really the challenge, is how fast could we image dynamic PET scans and reconstruct PET images to be able to make comparable or comparisons between these two simultaneous measures. So here's the experimental protocol. Down here on the right is the work from Villiers et al., where they simply showed a fixed visual stimulus, flickering checkerboard for 10 minutes duration, 10 minutes rest, and then another 5 minutes hemifield visual presentation, and so on. And so what we did in addition to that, as you see up here on the top in the green, was added a functional MRI stimulus, whereby in fact this 10 minutes of visual stimulus wasn't continuously on, but it actually started for a 2-minute visual presentation and then had the more classic fMRI type visual activation paradigm with 16 seconds of off and 32 seconds of on. So this was repeated a couple of times, as you can see, or in fact 4 times. So with this paradigm, it's possible to do a functional MRI analysis of individual 10-minute periods, or as well as the PET analysis to be done across the full 60 or 90-minute acquisition. And so here are the maps from the simultaneous acquisition. On the left is the fMRI bold map, and on the right is the functional PET visual cortex activation map derived from the analysis of 1-minute PET scans calculated across that 60-minute period. And there's obviously, great similarity, as you would hope, but there's also some differences, and I think that's of particular interest in terms of understanding the underlying true metabolic basis of brain activation studies. And it really goes towards ultimately validating the functional MRI data that's been published now for over 20 years that truly is underpinned by glucose, more direct neuronal metabolism changes. Here's a bit more information about that. So here you see the head curves again in a subject, the red being the whole brain and the blue being those areas in the visual cortex that were identified from the analysis, and you can see an increased uptake rate in those brain areas. Over here on the far right is the functional MRI map and the temporal signal, and then in this middle column is the functional PET map with the 90-minute, or I think it's 80-minute temporal duration of signal increase during visual stimulation, hemifield left, hemifield right, and at the end again another increase in the brain metabolism. So I think this is really fascinating. Now, one of the challenges with our MR PET is that our sensitivity is better than a typical PET CT. It's about 25 kilocounts per second, but it's not as good as the new generation of digital PET CTs that are coming out, which in fact I found out on the weekend. The Siemens Vision has a sensitivity of 85 kilocounts per second. So in fact, doing very fast dynamic PET imaging down to tens of seconds, and maybe, who knows, I don't know whether a second PET scan is really going to be possible, but from my point of view and from our experience, the technology is getting towards this point where you can do actually comparable temporal rates as to functional MRI, which I think is really fantastic. So just finally, this is some further analysis work from Shengpin Liu and Francesco Frosarini at MBI, looking at, again, trying to now do joint analysis de novo, looking at the spatiotemporal maps from fMRI and PET and doing a joint ICA to come up with joint estimates of these spatiotemporal maps, which are shown at least spatially here on the right-hand panel. So that's work in progress, and there was a poster today that Shengpin had up for those who would be interested. Okay, so I might just move on to this last section just to round out the other human work that I think is of importance with the MR PET, and that is with Ian Harding. He's a early career research fellow at Monash, and Ian's very interested in neurodegenerative diseases. I think that's another important area for simultaneous MR PET. There's the opportunity of elderly subjects or subjects with dementia only needing one scan. You get the structural information, a whole range of diffusion or multi-MR contrasts, and then you can also acquire the PET image. And in Ian's case, he's investigating Huntington's disease and he's using FEMPA to start to look at neuroinflammation markers in HD. So this study is in early stage as well, but he's scanned now getting towards 20 subjects and looking at SUV-based analysis of these whole brain, human brain images. And you see here some initial results where looking at areas of increased neuroinflammation or FEMPA marker in HD compared to controls, and then many areas of reduced FEMPA activity compared to in the patients compared to controls. Okay, so that's it. Thank you very much for your attention. I just want to acknowledge all of the group at MBI involved in this work, and I've pointed out many. Our collaborators, including Malin Premature in engineering at Monash, and Nelly Giorgio Christianis in psychology, and I've mentioned our other collaborators there on the right, and to also acknowledge our funding sources. Thank you for your attention.
Any questions or comments? So actually we have 5 minutes, so the first question is, I wondered, using MMR machine, within 30 minutes, you can simultaneously acquire FDG PET and also resting fMRI. So have you tried to use that in your scheme of comparison studies?
Yeah, we have actually. That was the second thing we started doing. Yeah.
Yeah.
So resting state fMRI and looking at the underlying, metabolic changes with dynamic or functional PET. Yeah, that's an area that we're working on. I think it's very interesting.
So, any questions? And then, please.
This ICU for the sheet, newborn sheet, how do you do the logistics for that? It must be really time-consuming and costly. Students who's watching over them?
Yeah, look, they have students. They have some great. It's a great team. They've dedicated to, the sheet model over many years. So they're very efficient. They have veteran vets on their staff. And yeah, they've simulated the whole NICU setup for monitoring and managing these lambs. I guess that's the other thing where we're located. It's not on a hospital site, so the animal models are set there and can go into a holding area, if you like, or a treatment area in the surgery, and be maintained for essentially 18 hours or thereabouts post delivery, including imaging. And that's probably a challenge in a hospital environment where the facilities are needed most of the time of the day. So yeah, that's one of the ways we've done it.
Please.
I really like your brain work, your human brain work. I have 2 questions. So we saw on rats when we do continuous infusion, and especially when we do a bolus injection or a continuous infusion, that the pharmacokinetic of the FDG really determines the pattern what we see after stimulus in the PET images versus the fMRI. The question is, have you looked at the pharmacokinetic variation? And my second question is, in the rats, so we do everything on animals.
Yep.
In the rats, we did C-phosphating, so EPI gene mapping, and we found that whatever we see in PET with FDG after stimulation is much more reflecting the immediate gene mapping, the C-phosphataning, compared to the fMRI. So it looks like what's good for us nuclear medicine guys, that the PET is much more accurate, independent whether we use a 7 Tesla fMRI or 14 Tesla fMRI than MRI. Is there any way that you could find out in patients or in humans what is the gold standard, what is the real truth?
Well, that's a great question. Thanks, Bern. And yeah, I mean, it's definitely part of our aspiration is to look at the essentially the differences between the metabolic PET maps, say in the visual system, and the fMRI maps. And there's clearly evidence that we've seen so far of vascular contributions in the MR that don't come out in the PET, for example. I think more comprehensive, whole brain vasculature imaging will be very helpful to underpin that. And the first point you made, sorry, what was that again?
That the pharmacokinetic
Oh yes, yeah.
really determines the pattern of
Yeah.
what you see later on.
So yeah, we've started to play around with the type of infusion so that it's not necessarily 100% of the dose given as a slow infusion. I think we can improve, the quality of the early images and get to a steady state sooner. We've done some whole blood analysis, but we haven't looked at metabolite analysis yet to look at the pharmacokinetics aspect of the actual FDG distribution. I mean, that's an interesting point. I think it is very important to be able to determine that the signal increase that we're seeing is coming about from, glucose uptake rather than metabolite redistribution. Yeah.
May I ask one thing on your first answer? So this means your hypothesis is that there is a pollution, let's say pollution or whatever, of the fMRI signal from the perfusion, which could cause the mismatch between...
Yeah, like it's more on the draining venule side, of course. So, fMRI being a neurovascular response, so one would expect it to be on the draining venule. And I guess the question is, how big a contribution is that to the fMRI signal? Without these sorts of measures, it's, I think, impossible to really know. But, I mean, I think the main message is that fMRI is mostly right. It's not like it's going to be completely wrong, but it's about how can we underpin, I think coming to the Chairman's question about resting state fMRI, that's a very important question, like what really are these resting state networks? What do they really underpin? There are a lot of correlations of bold sequence data across the brain. Is there an underlying metabolic glucose metabolism basis to that?
So you have discussed in your neuroimage data, the article in 2014. Not just the similarity between FPET and fMRI, but just a mismatch between FPET and fMRI. And while you're showing us the image, I found that the visual cortex is similarly activated. However, the thalamus posterior lateral part, some discrepancy there. So
yeah.
You would have discussed in your neuroimage paper.
Yeah, that wasn't our paper though. That was from MGH. Yeah, and they didn't do functional MRI, so they really just looked at the PET.
Okay.
Yeah.
Then thank you very much. Okay.
Okay. Thanks.
All right. Next speaker is the Professor Weibo Kai from University of Wisconsin at Madison. He will talk about the multimodality imaging. Please.
Thanks. First, I want to thank Anna for the kind invitation to participate in this molecular imaging track. We have an excellent team of speakers. I feel honored to be a part of them. And today I'm going to show you a little bit of what we did over the last 5 or 10 years or so on multimodality imaging agents. Now, our research is mostly focused on 3 different aspects. One is the development of new imaging agents. The other one is on nanoparticles, its applications for biomedical applications, as well as targeted therapy. So for all of this, our primary focus is on cancer, but we do work on other diseases because molecular imaging is really not specific for a certain disease. It's specific for a certain molecule, a certain protein, or certain overexpressed receptors. So in all 3 areas, we have done something related to multimodality imaging. So I'll show you a few examples of, for example, purely imaging agents, or nanoparticle-based multimodal imaging, as well as therapy that incorporates multimodality imaging. This is the hallmarks of cancer. I think we're all very familiar with that. One of them is angiogenesis, which is the formation of new blood vessels from the already existing blood vessels. And during this process, there are a lot of different proteins or receptors that could play a role during angiogenesis. So a few years ago, we wrote a review. Basically, in that case, we covered all the radio-labeled agents that are used for both preclinically and clinically that are used to image vascular targets. And those are not only limited to cancer, not only just tumor angiogenesis, but also cardiovascular disease and inflammation. So our group, we have spent quite some effort on 3 of those targets. For example, we can use RGD peptide to target integrin alpha beta 3. We can also use VEGF to target VEGF receptors. And over the last 7 or 8 years, we have also done quite a bit of work targeting CD105, which is one of the overexpressed receptors on the tumor neovasculature. So for the targeting, we use an antibody called TRC105. The TRC comes from the name of the company, and 105 comes from the CD105. It's a chimeric antibody. The antibody is already in phase 3 trials now in the United States. So hopefully in a few years, it could get approved by the FDA as an anti-cancer agent in combination with some other agents. As a control, we use cetuximab. It's a human murine chimeric IgG1 monoclonal antibody. It's the exact same isotype, but it does not have anything, does not bind to anything of murine origin. It only binds to the human EGFR. So this serves as a perfect control when we use a totally murine model, the commonly used 41 murine breast cancer model. We know that it expresses high level of CD105 based on previous studies. So I've labeled TRC105 in many different ways. I'll just show you one example. In this case, we dual label TRC105 with zirconium-89 through desferol. We also label this with a near-infrared fluorescent dye, so you can use this for both PET imaging and MR imaging. And for the model, we use this experimental lung metastasis model. So we inject the cancer cells intravenously. They got trapped in the lungs, and the cells are transfected with firefly luciferase. So we can monitor the animals over time to pick the animals at the right stage for this kind of imaging, because if the tumors are too small, there are not much angiogenesis ongoing. If the tumors are too large, because it's in the lung, the animal will die quite soon. So there's very narrow window of imaging. So this bioluminescence imaging is really convenient to pick the right tumor kind of the right animal at the right tumor stage. And when we're doing vivo imaging, we can see clearly see the different nodules in the mouse lung. And we also did ex vivo imaging. Here shows the ex vivo imaging of the major tissue. So those are the exact same tissue scanning in 3 different ways. One is that, so here is the lung, we can see based on the bioluminescence. So we have to do it really quickly within maybe 5 minutes or so after we get the tissue. We can clearly see the multiple nodules of the luciferase expressing 41 tumor. And for PET, we can see the lung signal here. And for fluorescence, we can also see the signal. So the fact that those matches quite well, indicating that the labeling is it's quite stable in vivo, and also they are mostly localized in the lung. So it's imaging the angiogenesis on the vasculature. We also have histology to confirm this. Of course, optical imaging, you can also use that for image-guided surgery. This is just in animal models. We can use a Bob C mice that has hair, so the image looks a little bit lousier. When we use the lewd mice, the image looks a little bit cleaner. We can wait 24 hours, and we can remove the tumor, surgically remove the tumor, and we can scan the animals again. We can also harvest the tissue to make sure there's no tumor tissue left at the original site. But this is 24 hours, so there's still some signal left in the tumor site, but that's because of the blood signal, because it's still circulating. It's not really because of the residual tumor. So over the last 10 years also, we worked on a variety of different targets, some including angiogenesis-oriented, some are more focused on cell surface receptors. And this morning, there was an excellent plenary session on immunotherapy. We have also done quite a bit of work on different targets, including PD-1, PD-L1, CTLA-4, as well as interleukin-2 and 15. That's a little bit less studied target. That's in collaboration with a company. We have also worked on many other targets. So for our group, most of the targeting ligand we use are biological molecules. So all the way from small peptides, say RGD peptides, to antibodies, or antibody drug conjugates, or some antibody fragments that's somewhere in the middle. We can also express certain proteins. And for example, we can express VEGF to image VEGFR. We can also express hepatocyte growth factor HGF to image CMET. We have also done quite a bit of work in that area. And now that we have the single targeted agent, we can also do a dual targeting, because cancer is a heterogeneous disease. You can't expect to do one single targeting and then kind of cure the cancer. So I've tried a few studies in this area. We have to pick the right target. And in this case, we use a cetuximab Fab, which binds to EGFR that's overexpressed on the human cancer cells. The TRC105 Fab, it binds to CD105 that's overexpressed on the tumor neovasculature. We can link those two together through a commercially available agent, TZ and TCO, through click chemistry. We have this bispecific Fab2 fragments, and this one radio label them. We can do both mono labeling and dual labeling. For example, with a PET, if we label with a PET trace copper 64, we can see the dual targeted group has much higher signal compared to the control groups. Optical imaging, we can do cell-based studies. We can also use optical imaging for image-guided surgery, just like I showed you previously. So we have done multimodal imaging through kind of either proteins or nanoparticles. So those are a few examples of the protein or antibody-based dual modality imaging that we've done before. So for the rest of the talk, I'll focus on nanoparticle-based work. That's a little bit more flexible. We can label it with different ways. You can also do drug loading, and also you can do a different kind of therapy. I will show you a few examples. That's a review I wrote in JNM a few years ago on theranostic nanoparticles. There are many different nanoparticles that can be used for all kinds of different applications. Some are for imaging, some for therapy. And there are inorganic nanoparticles, organic, self-assembled, something that can respond to extra stimuli. Basically, pretty much everything you can think of, probably somebody is doing that with different kind of nanoparticles for biomedical applications. So the previous two speakers were mostly focused on PET-MR, so I thought I'd just like to maybe take a short break from PET-MR. So I'll talk a little bit about PET optical, and then I'll still go back to PET-MR and move beyond just PET-MR. Here shows just one. I'll show you some of the examples. Fen Chen is a postdoc in my group. He's now in Memorial Sloan Kettering working in Michelle Bradbury's group using radio-labeled CDOTs for clinical translation. And when he moved to our group, his PhD was on making different kind of nanostructures, including, for example, mesoporosilicon nanoparticles or upconversion nanoparticles, iron oxide nanoparticles. So he has a material chemistry background. When he moved to our lab, so we kind of take advantage of his previous expertise, say the nanoparticle synthesis, and also kind of in conjunction with our strengths, which is radio labeling, in vivo imaging, tumor targeting. And we came up with some project in the middle so that it's easy for him to pick up, to catch up. So on my title slide, those images are the TEM images of the nanoparticles that he made in our group for different kind of applications. And for multimodality imaging, I think each imaging technique is there to serve a purpose. It has to tell you some information that hopefully the other imaging technique cannot tell you. I'll just show you one example here. The mesoporosilicon nanoparticles that he made, he has made this during his PhD study. In China, he has done this drug loading therapy studies, but he did not do any radio labeling or tumor targeting, which is our strength. So we kind of the first project that he did was using this mesoporosilicon nanoparticles. We can load it with a drug, and we can use that for targeted drug delivery. For drug delivery, we can also link this with TRC105, which is binding to the tumor vasculature CD105. We can also label it with copper. So we can do a quantitative imaging, and also it's quite, there's no tissue penetration limit. So it could potentially be clinically translated if we have the right resource and the right facility. So here shows the TM image of the mesoporosilicon nanoparticles. As a model drug, we use doxorubicin, which is fluorescent. So we can easily measure how much drug is loaded into the nanoparticle. And also we can measure the drug release through the signal of the doxorubicin. It's also pH responsive. So here it shows the in vivo imaging data based on PET. You can see the tumor signal in the targeted group is much higher than the non-targeted group or the blocking group. But this, you are only imaging the radioisotope. You are not really imaging the nanoparticle itself. So if the nanoparticle labeling is not very stable, the PET image may not tell you where the nanoparticle is. So typically, whenever we do any radio labeling of nanoparticles, we always do at least two different kind of imaging techniques. One is that we can image the nanoparticle itself, or we image the PET through the radioisotope. The other one is that we can either image the nanoparticle itself, or we can image the drug that was loaded into the nanoparticle. So we measure those both separately, and then compare the data. If the data matches with each other quite well, that gives us confidence that the data is indeed quite reliable. The nanoparticle is intact. It's kind of they all stay together in vivo. So here it shows the PET signal that's relying on the copper. Here it shows the optical signal that's based on the fluorescence of the doxorubicin that was loaded inside the nanoparticle. The dox has a visible range of fluorescence, so it does not do very well for in vivo imaging. So we did ex vivo imaging. Here it shows the ex vivo images of the targeted group on top and the non-targeted on the bottom. You'll see that the tumor signal is definitely higher in the targeted group compared to the non-targeted group, which is kind of what we would expect. When we quantify this based on the IVIS system, that's about 2 to 3-fold enhancement, which is matching quite well with the PET data, suggesting that it's quite stable in vivo. What's really interesting is that you'll notice that here, those are kind of the same group of animals. It's the same tissue, but here it shows much higher signal in the liver, while here you'll see that the liver signal is much lower than the tumor. That's kind of misleading if somebody do not have enough experience with optical imaging, because the doxorubicin is in the visible range, while liver is quite dark colored. So both the absorption, the excitation light, and the absorption and the emission light will be highly absorbed. So it looks like the liver signal is quite low, but actually the absolute amount of doxorubicin is much higher compared to the tumor, which is kind of because those are the same animals. So typically we always have to measure both things and then cross-validate, make sure the data is reliable. So also, especially we need to be careful about quantification of the optical signal, because that depends on the length, depending on the depth, depending on the color, depending on many other things as well. The other area that we worked on is kind of making nanoparticles, label it differently so that hopefully it's much easier so we can do clinical translation. This is something we call intrinsically radio-labeled nanoparticles. That's a review we wrote about 4 years ago. We covered every single paper that we could find until that time. Basically, generally when we label the nanoparticles, we label it using, because F18 is kind of too short, so it doesn't work very well in most cases. We want to image longer, so usually we label with radiometals, say copper or zirconium or some other nanoparticles, other radioisotopes. But these typically need a chelator, and then you need to do purification, so it's kind of more complicated. It's harder to do translation. So we spent quite some effort over the last 5 or 6 years trying to make it simpler, make the nanoparticle labeling simpler so it has a better chance of clinical translation. Because the biggest hurdle for nanoparticle in clinical work is that if you want to translate into the clinic, you want to know how long it stays in the long-term toxicity, the clearance. Those are really important. And I think PET is the best way to measure those non-invasively because it's quantitative and also there's no tissue penetration limit. In animal models, you can do ICP-MS or you can do some other studies to measure nanoparticles, but you can't do that in patients. So I've spent a lot of effort on this something called intrinsically radio-labeled nanoparticles. And one area is called the specific trapping. When we started on this about 6 or 7 years ago, we thought, what is the starting point? That goes back to the PET-MR. That's when the PET-MR just became a commercial PET-MR, just became a commercial, the clinical PET-MR just became commercially available. So we thought if you have a new PET-MR scanners, you need new PET-MR agents. And actually this project was the very first project I wanted to do when I joined the UW as a faculty, because we know that iron oxide absorbs arsenic very tightly. And we have a collaborator, Professor Jerry Nichols' group, that has made radioactive arsenic. So we know iron oxide absorbs arsenic very tightly, so just simple mixing, you get a PET-MR agent. But we just can't do that in the beginning because our group, we just don't have the expertise to make those nanoparticles. So once Fen Qian moved to the lab, that was his first also his first project, in addition to the silica-based nanoparticles. And this work only took him a couple weeks or less than a month. Basically, we just make those, he can make those iron oxide nanoparticles. Our cyclone group can make those arsenic. We know that they bind to each other very tightly. There was a 2004 science paper about that, the mechanism and the details. So we don't need to figure out the details. We just know it works. And when we mix those together, you end up with a PET-MR agent. We can also do sentinel lymph node mapping, just like Dr. Lee just mentioned, kind of to confirm that indeed this can work in vivo. So here, the PET signal, PET's image is detecting the radioactive arsenic, while the MR is detecting the iron oxide. On one side, this side is the control, the lymph node does not change, while the other side, when it was injected, initially the lymph node is bright. When iron oxide goes there, it gets much darker. Of course, we also have to inject larger amount of iron oxide nanoparticles because MR has a relatively lower sensitivity. We have also tried a few other radioisotopes. For example, germanium-69. This is something that few people have studied because it's just hard to label because it exists in different forms in the aqueous medium. So we thought maybe we can use nanoparticles to label this. This was actually inspired by the clinically used germanium-gallium generators. When you elute gallium out, you don't want germanium to come out. And the way to trap those germanium on the column, there are many different ways. One way is to use metal oxide nanoparticles to trap those. So this, so iron oxide is also a metal oxide nanoparticle. So it actually worked quite well. That's the TEM of the iron oxide. When we mix it, we can do a simple radio TLC. When germanium is on the iron oxide nanoparticle, it does not move on the radio TLC. But if it's not labeled, it'll move to the solvent front. So simple radio TLC, we can calculate the EOT, we can optimize the reaction conditions. And this was actually spearheaded by Ruba Chakravarti. he was a Fulbright scholar from India. He went to my group for about a year, and what his work back in India was actually to make germanium gallium generators that can trap germanium much better, so that when it loses, you don't have the germanium coming out. So again, it's kind of a combination of his previous expertise along with our kind of a facility or our capability. To confirm that it's indeed specific for the iron oxide surface, here shows some of the control experiments. When we have the iron oxide coated with polyacrylic acid, we can label it easily. But if we coat the iron oxide nanoparticles with a layer of dense silica, so even though you have iron oxide, but it's all wrapped inside tightly, it's not exposed to the surface, it does not label. If we use another nanoparticle, say copper sulfide, that's not a metal oxide nanoparticle, it also does not label. So indicating that it's specific for the iron oxide surface that has to be exposed to the surface for this germanium labeling. So again, kind of similar studies, we can do PET and MR, and PET is measuring the germanium, MR is measuring the iron oxide. We make sure those two data matches with each other so that we confirm that it's stable in vivo. Even the labeling is very simple, just simple mixing. There's really no method if we're strictly speaking. This is again the lymph node mapping, just like I showed before. So over the last 10 years also, we have worked on a variety of different isotopes. Professor Jerry Nichols and his former trainees, say Todd Barnhart or John Engel, they made over 100 different isotopes over the last 4 decades since Jerry moved to UW-Madison. But before I moved to Wisconsin, very few people, if any, at UW-Madison was actually doing this kind of study with isotopes. So they made it, they characterized it, but nobody is doing the kind of subsequent work, biomedical applications. So for me, that's really like a gold mine. It's like when people initially moved to Melbourne because there's gold here. So we have published, we have different kind of isotopes we can use. They have different half-lives, so that when we label the right thing, we can pick the right isotope. If we label a short-lived agent, for example, antibody fragment or a small protein, we can use copper-61, has a 3-hour half-life, or scandium-44, that's a 4-hour half-life. If we want to label longer-lived, say, want to do long-term imaging, we can use zirconium-89 or manganese-52. But let's say if you're not in Wisconsin, you can only buy radioisotopes. Most of the isotopes you can buy in the US are typically just copper and zirconium. So even when I was a postdoc at Stanford, we actually bought the copper all from Wisconsin. So now that I'm out of Wisconsin, I don't really, we collaborate with each other, so it's much easier. And also, the data we get is always 1 day earlier than our competitors because they ship the isotope FedEx overnight to the other people. So if we're doing the exact same thing, we don't worry too much about we're a little bit too late. So we have done intrinsic radio labeling to all those isotopes, actually, but I don't have time to show you the details. But I'll just show you 2 examples on copper and zirconium because we really want this method to be broadly applicable so that hopefully other people can use that as well. So talking about zirconium-89, we can use desfro as a chelator that has oxygen. We have also worked with mesoporous silicon nanoparticles that has a lot of oxygen in it because it's silicon dioxide. So this could be, we were thinking maybe this could be used for intrinsic labeling without any DOTA, NOTA, or desfro. It actually worked very well, and because it's a mesoporous silicon nanoparticles, the zirconium are mostly inside the meso channels, so it's not exposed to the outside. This is quite stable in vivo. And we actually scanned the same group of mice over 6 half-lives, so about 20 days, and we found very little uptake in the bone, indicating that it's quite stable, because if the zirconium falls off, you'll see some bone uptake. The labeling is simple, and time and concentration are dependent. So after that, we moved beyond to a little bit more complicated systems using this method. We have also done something kind of a little bit more complicated, though in one direction, we try to make it easier so that it's simpler for potential translation. On the other side, we can also design agents that can respond to, say, certain external stimuli or can respond to some tumor microenvironment. And usually for all of those, we do some PET imaging in it. So I'll just show you some examples. We do a lot of work on combination of PET with different kind of nanoparticles for different kind of applications. Some could be imaging therapy or integration of those. There's something called theranostics. I'll just show you this example. That's a hollow mesoporous silicon nanoparticles. It's like the mesoporous silicon nanoparticles, but it has a large cavity inside. So it can serve as a reservoir to load the drugs. We can label zirconium on the first step and carry it all the way through without losing any zirconium because the labeling is so stable. When we functionalize this with amine groups, it's positively charged. We can make copper sulfide citrate that's negatively charged. So the charge-charge interaction, they form this kind of core satellite nanoparticles. Copper sulfide can be used for photoacoustic imaging as well as photothermal therapy. While TCPP is a photodynamic dye that can be used for photodynamic therapy. At the very end, we put on a PEG of 10,000 molecular weight, so it's more biocompatible, has better circulation lifetime, so it has more EPI effect. So for this nanoparticle, it has a different kind of imaging. We can use different imaging techniques. PET is imaging zirconium. Fluorescence is imaging TCPP. Cherenkov is optical imaging of zirconium, while we can also use the Cherenkov signal to excite TCPP. So that's a Cherenkov resonance energy transfer. And for the treatment, we have two different treatment techniques: photothermal therapy, PTT, using copper sulfide; photodynamic therapy, PDT, using TCPP. And this is the TM images of the nanoparticles. So this is about 150 or so nanometers in diameter of the hollow MSN. Copper sulfide, like 3 nanometers or so in size. So there are hundreds of copper sulfide. Each of the small dots is a copper sulfide. And we use 980 laser for the photothermal of using copper sulfide. We use 660 nanometers for photodynamic therapy, which is exciting the TCPP. And here shows the labeling. It's quite pure, and those are the 4 different imaging techniques that are detecting different kind of aspects of this agent. And we can also do the in vivo kind of combination therapy, and we found that it was highly synergistic. So if we use just PTT or PDT alone, we can kind of lower the kind of the strength of the PDT or PDT, so that by itself it can only slow down the tumor growth or stop the tumor growth, but it does not shrink the tumor. But if we combine those two together, it can shrink the tumor very quickly and it doesn't come back. We also calculate the synergistic effect to make sure they are more than just additive. So 1 + 1 is much greater than 2. Here shows the statistical analysis. So all the animals survived in this group, but all the animals in other groups eventually kind of have either when the tumor reaches a certain size or they died because of the tumor is too large. So those are the staining images to confirm the photothermal and the photodynamic effect. So that's one example about zirconium labeling of silica-based nanoparticles. We have done a whole series of silica-based nanoparticles with intrinsic radio labeling of zirconium. So actually, Fen Chen is now at the Memorial Sloan Kettering. They were using zirconium to label CDOTs using a similar method, because CDOT is also made of silica. And they actually just did the clinical studies of those. So actually, it is moving to patients, those kind of method, although it's not out of Wisconsin. But nonetheless, I think I'm happy that the same method or the similar method has actually made a difference into the clinic. So that's about copper labeling. We have also done that's about zirconium. We have also done copper labeling. This is kind of photoacoustic imaging. You've heard a lot of it already, so I want to show you that. But basically, this is in collaboration with a group at the University of Buffalo. They want to use photoacoustic imaging to image the functional properties of intestines. So they are focusing on digestive disease, so not the cancer that I was talking about. Here, this molecule absorbs light very intensely, so it's a great photoacoustic imaging agent, but it doesn't dissolve in water with a log P of more than 8. But if you put that in the micelle, it will go into the central hydrophobic part of the micelle. The beautiful thing about this micelle is that the pluronic F127 is commonly used agent that is in a lot of FDA-approved agents. This one, the critical micelle concentration is dependent on the temperature. When you lower the temperature, the critical micelle concentration goes up, so all the micelles will fall apart, unless it has this very hydrophobic molecule that stays in the middle. It just acts like a superglue, so it cannot be disassembled. So we can do dialysis to get rid of all the monomers. So we end up with very high concentration of those micelles. Each micelle has a lot of those molecules in it, and each molecule absorbs light very intensely. So it's very good for the photoacoustic imaging. Size is about 20 or 30 nanometers. When you use different R groups, you can cover the entire infrared range. Because we're imaging intestines, after oral gavage, we can collect 100% of those in the mouse feces. And the photoacoustic imaging gives you good spatial resolution and good temporal resolution. We can see the mouse intestine contract about 30 times a minute. That's exactly what it should be, but it does not give you good tissue penetration. Here it shows, so this is a structure. There's M in the middle that stands for metal. If we use radioactive metal, say it's copper 64, so we can just, after we make those agents, we just mix with copper. Half an hour later, we have this labeled agent. It's also quite stable. Going through the stomach, and we can collect 85% or more of the radioactivity through the feces, so indicating that even though it's very simple labeling, it's quite stable. And here shows the PAT, photoacoustic. Here shows the PET. They have a different kind of properties. Each has its own advantages and disadvantages. The exact same agent, without doing anything, we just change the laser intensity. We can do also photothermal therapy. So aside from PAT and PET, we have this PTT. Now this can shrink the tumor growth very easily. If we apply another one, we can shrink the tumor growth again. We also moved one step further. This is totally natural. That's chlorophyll. It's in the green vegetable that we eat. And here there's this manganese in the middle. We can remove the manganese. Now there's 4 nitrogen that can be used for copper chelation. So exact same method like I showed you before. We have this radio-labeled micelle with this chlorophyll derived agent in the middle. The good thing about this is that chlorophyll itself is not fluorescent, but once you remove this manganese, now it's fluorescent. So aside from PET and the photoacoustic, we can have fluorescence. So that adds one more function that you could use it for image kind of superficial agent or superficial tissue, or you can use that for image-guided surgery. So this is the last example I'm going to show you. We can make a very simple agent that can be imaged with 6 different techniques. This is based on upconversion nanoparticles with a porphyrin phospholipid, which also has 4 nitrogens here for copper labeling. So this self-assemble into this nanoparticle, size is about 50 nanometers or so. And we can use that for imaging on 6 different techniques. That's fluorescence, upconversion, which is based on the upconversion nanoparticles. PET is based on copper 64. If we inject a large dose, this also gives you a CT contrast and Cherenkov luminescence and also a photoacoustic imaging. But we are not doing this 6 just for the sake of getting a 6 modality into 1 nanoparticle. They actually tell you different information. If you look at the signal here, if you look at upconversion luminescence, or the PET or CT or Cherenkov luminescence, the signal are about the same. So there are 3 tubes here. This is just water, blank. But the other 2 tubes, one has detergent, one does not have detergent. You'll see that the signal are very much the same in some of those, but in the other one are different. For example, fluorescence. That's because when this molecule, it is fluorescent by itself. When it is self-assembled on the nanoparticle, they are too close to each other, so they call self-quenching. So the fluorescence signal is actually lower, but the photoacoustic signal is stronger. But if it falls apart, the fluorescence signal will become stronger, but the photoacoustic signal will be weaker. So that can tell you the status in vivo, whether it's disassembled or whether it's still stable. So the photoacoustic and fluorescence, you'll see that give you exact opposite information that can tell you the status of that in vivo. So not just doing 6 for the sake of 6. We could have easily doped the gadolinium for add another MR to this, but the kind of probably does not really, it's not really necessary. So we did a very detailed comparison of the penetration, resolution, kind of a depth, and also quantitation. So basically, I think the conclusion is it's kind of what we already expect. It's a very simple agent. We're just mixing 2 components together. You end up with imaging agent that can be imaged with 6 different modalities, and then fluorescent and photoacoustic can tell you whether it's stable or not, whether it's self-assembled in vivo, or whether the surface coating has already fallen apart. While PET and CT can give you a different tissue penetration or the resolution. So just to conclude, different imaging techniques, I think they're really not competing against each other. We need to use them properly, so at least it should be complementary, which is 1 plus 1 equals 2. Ideally, I definitely want that to be synergistic, which means they really can tell you much more things than they are just simply additive together. So I'd like to thank a lot of people, our Cyclone group, my former supervisors, my collaborators, funding agencies, and the companies we work with, and those are the people that did the work. And thank you very much for staying here on a sunny afternoon. Thanks.
Okay. As always, you would have been overwhelmed by the quantity of the data. And because of the time, one quick comments or question. Or I'd like to.
Let's take a
because
break.
we have full armamentarium of imaging modality and also materials, intrinsically labeled or chelator-based label. So, do you think that how the next step would be how to find the not multimodal, oligomodal theranostic agents for in vivo use?
I mean, if you ask me if I want something that I want to translate at UW, I think the column labeled silica, biodegradable silica nanoparticles,
yes.
that would be the way to go. But we just don't have the infrastructure or the facility or the funding to do that.
Yeah.
Because for nanoparticles, at first the agent has to be non-toxic, so silica is definitely better than heavy metal-based.
Yeah.
Second, it has to be either clear or biodegraded, and we can make biodegradable silica nanoparticles that can degrade over time. And the labeling, I think the zirconium labeling is so simple and it's quite stable, and it can tell you the clearance or the biodistribution. So that's the one that if I have say if somebody give me a $10 million check, I'll do that.
I just pretended to be a devil's advocate. Why? Because we are at clinical side,
Right.
so we cannot do the every experiment in humans.
Of course, yeah.
Yeah. Thank you. Thank you very much.
Thanks.
Thank you for your time. Okay.